In the name of Almighty God, I'm Mahsa Sankashi, and today I want to talk about the acoustics module physics interfaces. There are nine main branches: pressure acoustic, elastic waves, acoustic structure interaction, aeroacoustics, thermoviscous acoustics, ultrasound, geometrical acoustics, pipe acoustics, and acoustics streaming. And each of the physics interfaces is briefly described here, followed by the physics interface guide by space dimension and study type, listing the physics interface availability by space dimension and preset study types. The chapter of pressure acoustic. The pressure acoustic branch has interfaces where the sound field is described by the pressure P. The physics interface solves acoustic problems in the frequency domain using the pressure acoustics. Frequency domain interface where the Helmholtz equation is solved. Transient systems are modeled using the pressure acoustics transient interface where the classical wave equation is solved. Nonlinear effects can be included here using the nonlinear acoustics Westerveld feature. The boundary mode acoustics interface is used to study propagating modes in waveguides and ducts. At a given frequency, only a finite set of wave shapes can propagate over a long distance. The figures 4 scattered SPL at a submarine hull modeled with the asymptotic scattering formulations. To efficiently solve large radiation and scattering problems, the pressure acoustics boundary element interface solves the Helmholtz equation using the boundary element method or beam. The interface is fully multiphysics enabled and coupled seamlessly with the finite element based interfaces, both acoustic and structural. The pressure acoustics time explicit interface uses a time explicit method based on discontinuous Galerkin finite elements to efficiently solve large transient problems. The physics interface can also be solved on a GPU. It can also be coupled to the elastic waves time explicit interface. Porous domains can be modeled in the time domain with this interface. Finally, two interfaces exist to model high frequency acoustics: the pressure acoustics asymptotic scattering interface for scattering problems, and the pressure acoustics Kirchhoff-Helmholtz interface for radiation problems. Figure 5 shows a three-dimensional bubble plot of the loudspeaker radiation pattern at 3000 Hz from the vented loudspeaker enclosure model found in the application library. The model uses a hybrid FEM-BEM modeling setup. A large variety of boundary conditions are available, including sound hard walls and conditions for applying sources. There are radiation symmetry, periodic, and port conditions for modeling open boundaries. Impedance conditions include models for different parts of the human ear, human skin, simple RCL circuit models, and more. Frequency-dependent impedance conditions in the time domain can be set up. Using the built-in rational fitting approach, the physics interfaces also have several fluid models, which in a homogenized way mimic the behavior of sound propagation in more complex media. This includes the propagation in porous or fibrous material, the poroacoustics and anisotropic poroacoustics domain feature, the propagation in narrow structures of constant cross-section, the narrow region acoustics domain feature, and fluid models for defining bulk absorption behavior. Monopole, dipole, and quadrupole point sources can also be applied. So-called perfectly matched layers (PMLs) are also available to truncate an unbounded computational domain in both time and frequency domain. Finally, the exterior fit calculation feature can be used to determine the pressure in any point outside the computational domain. Dedicated results and analysis capabilities exist for visualizing the radiation pattern or of the exterior field, near and far field in polar two-dimensional and three-dimensional plots. The chapter of elastic waves. The elastic waves branch includes physics interfaces and multiphysics interfaces for modeling the propagation of linear elastic waves in solid porous materials and piezoelectric materials. If necessary, the interfaces are readily coupled to fluid domains using the built-in multiphysics couplings. The physics interfaces under this branch are the first solid mechanics elastic waves for modeling elastic waves in solids. The port boundary condition is specifically implemented to model and handle various propagating modes in elastic waveguide structures. The second one is poroelastic waves for precisely modeling the propagation of sound in a porous material, isotropic and anisotropic. It includes the two-way coupling between the deformation of the solid porous matrix and the pressure waves in the saturating fluid. The physics interface solves Biode's equations in the frequency domain using a UP formulation. It includes two formulations for the loose mechanisms. The Biot viscous losses for modeling rocks and soils, and Biot Allard or Biot GCA that includes thermal and viscous losses for sound absorbing materials in air. The next one is elastic waves, time explicit, for modeling the propagation of linear elastic waves in solids using discontinuous Galerkin time explicit formulation. The interface is suited for modeling large problems with a memory efficient method. The next one is piezoelectric waves, time explicit multiphysics interface for modeling linear elastic waves in piezoelectric materials using the discontinuous Galerkin time explicit formulation. The interface is suited for modeling large problems with a memory efficient method. The chapter of acoustic structure interaction. The acoustic structure interaction branch has interfaces that apply to phenomena where the fluid pressure causes a load on the solid domain and the structural acceleration affects the fluid domain across the fluid-solid boundary. The physics interfaces under this branch are the first acoustic solid interaction frequency domain and acoustic solid interaction transient multiphysics interfaces. The next one is the acoustic shell interaction frequency domain and acoustic shell interaction transient multiphysics interfaces. The next one is acoustic piezoelectric interaction, frequency domain, and acoustic piezoelectric interaction, transient multiphysics interfaces, which support solving and modeling the electric field in a piezoelectric material. The piezoelectric coupling can be in stress charge or strain charge form. The next one is acoustic solid poroelastic waves interaction and acoustic poroelastic waves interaction multiphysics interfaces. The next one is acoustic solid interaction, time explicit multiphysics interface, and the next one is the multiphysics interfaces consist of two or more single physics interfaces. For example, pressure acoustics, frequency domain, and solid mechanics together with a multiphysics coupling. Here the acoustic structure boundary coupling. Many more couplings are supported, for example, coupling pressure acoustic to membrane or multi-body dynamic interfaces. Figure 6 illustrates loudspeaker driver simulation in three-dimensional including all multiphysics effects. The chapter of aeroacoustics, detailed convected acoustics, flow-borne noise sound that simulates the one-way interaction of a background fluid flow with an acoustic field is modeled using the physics interfaces found under the aeroacoustics branch. The coupling between the fluid mechanics and the acoustic is based on solving the set of linearized governing equations using stabilized finite elements methods. In this way, you solve for the acoustic variations of the acoustic variables on top of a stationary background mean flow. Different physics interfaces exist that solve the governing equations under various physical approximations. The linearized Navier-Stokes frequency domain and linearized Navier-Stokes transient interfaces are used for aeroacoustics simulations that can be described by the linearized Navier-Stokes equation solving for the acoustic variations in pressure, velocity, and temperature. The linearized Navier-Stokes boundary mode interface is used to compute the and identity propagating and non-propagating modes in the waveguides and ducts in the presence of background. The linear Euler frequency domain interface and the linearized Euler transit interface solve the linearized Euler equations. They are used to compute the acoustic variations in density, velocity, and pressure in the presence of a stationary background mean flow that is well approximated by an ideal gas flow. The linearized Euler boundary mode interface is used to compute and identify propagating and non-propagating modes in waveguides and ducts in the presence of a background flow. The linearized potential flow frequency domain and the linearized potential flow transient interfaces model the interaction of a stationary background potential flow with an acoustic field. These physics interfaces are only suited for cases where the flow is inviscid and being irrotational has no vorticity. The background flow is typically solved for using the compressible potential flow interface. The linearized potential flow boundary mode interface is used to study boundary mode acoustic problems, identifying propagating and non-propagating modes in a background flow field. It is typically used to define sources at the inlet of ducts using the port boundary condition. The imported fluid flow interface is used to map imported fluid flow data in the CGNS format onto an acoustic mesh. The interface also integrates with the necessary multiphysics couplings. Thermoviscous acoustics chapter. The physics interfaces under the thermoviscous acoustic branch are used to accurately model acoustics in geometries with small dimensions. Near walls, viscous and thermal boundary layers penetration depths exist. Here, viscous losses due to shear and thermal conduction become important because of large gradients. For this reason, it is necessary to include thermal condition effects and viscous losses explicitly in the governing equation. Thermoviscous acoustics is, for example, used when modeling the response of small transducers like microphones and receivers. Other applications include analyzing feedback in hearing aids and in mobile devices, or studying the damped vibrations of MEMS structures. In this case, a coupling exists to the thermoelasticity interface for detailed damping assessment. In the time domain, nonlinear effects can be modeled using the nonlinear thermoviscous acoustic contributions feature. Because a detailed description is needed to model thermoviscous acoustics, the physics interface simultaneously solves for the acoustic pressure P, the particle velocity vector U, and the acoustic temperature variation T. The figure 7 shows the formation of the diaphragm or membrane and internal pressure distribution at 125 kHz in the axisymmetric condenser microphone model found in the application library. In the thermoviscous acoustic frequency domain interface, the governing equations are implemented in the time harmonic formulation and solve the frequency domain. The interface is given in the scatter field formulation. Both mechanical and thermal boundary conditions exist. The interface exists in a time domain formulation. The thermoviscous acoustic transient interface, the thermoviscous acoustic boundary mode interface is used to compute and identify propagating and non-propagating modes in a waveguides and ducts. The interface performs a boundary mode analysis on a boundary, inlet, or cross-section of a waveguide or ducts of small dimensions. The thermoviscous SLNS approximation interface uses the fast approximative formulation of the equations that is valid in most cases. Several multiphysics interfaces involving thermoviscous acoustic also exist. The first one is acoustic thermoviscous acoustic interaction frequency domain multiphysics interface that include pressure acoustics frequency domain and acoustic thermoviscous acoustic boundary feature coupling the thermoviscous acoustics domain to a pressure acoustics domain is also straightforward with the predefined multiphysics condition. The next one is the thermoviscous acoustic solid interaction frequency domain multiphysics interface is available to solve coupled vibroacoustic problems. This can, for example, be used to model small electroacoustic transducers or damping in MEMS devices. It includes solid mechanics and predefined multiphysics coupling to the thermoviscous acoustics. The thermoviscous acoustic shell interaction frequency domain multiphysics interface is used for modeling the interaction between shells and acoustics in small dimensions. This can, for example, be used to analyze the damped vibrations of shells in hearing aids and prevent feedback problems. The thermoviscous acoustic elasticity interaction frequency domain and the thermoviscous acoustic thermoelasticity interaction transient interfaces are specialized multiphysics interfaces for modeling the coupled effects of viscous structural and thermal damping in a vibroacoustic setup. The chapter of ultrasound. Two dedicated interfaces exist under the ultrasound branch. The first one is the convected wave equation time explicit interface, which is used to solve large transient linear acoustic problems containing many wavelengths in a stationary background flow. In general, the interface is suited for modeling the propagation of acoustic signals over large distances relative to the wavelength, for example, linear ultrasound problems. Application areas include ultrasound flowmeters and other ultrasound sensors where time of flight is an important parameter. The next one is the nonlinear pressure acoustics. Time explicit interface is used to model the propagation of high amplitude nonlinear acoustic waves. Special functionality exists to capture shocks. Application areas include biomedical applications, for instance, ultrasonic imaging and high-intensity focused ultrasound. The applications are not restricted to ultrasound. Both interfaces include absorbing layers that are used to set up effective non-reflecting like boundary conditions. Both interfaces also couple to elastic waves time explicit using built-in multiphysics couplings. The interfaces are based on the discontinuous Galerkin method and use a time explicit solver. The method is very memory lean. Thank you so much for watching my tutorial video until the end. Today is the 11th of the March 2026 and the time is 10:41 in the night that I'm recording this video for you. Also, you can download the proper and appropriate file related to this ultrasound and acoustic pressure module from github.com/mahsascript.